The operational geometry of the Western Pacific has been reshaped by a deliberate and sustained Chinese military modernization campaign designed to push American air power beyond the first island chain. The sanctuary model that defined 3 decades of U.S. air operations, under which tankers, command and control aircraft, and forward air bases could be positioned with relative impunity, is no longer militarily credible. China's anti-access and area denial architecture now extends across the South China Sea and well into the Philippine Sea, anchored by the DF-21D and DF-26D anti-ship ballistic missiles, a proliferating fleet of hypersonic weapons, and a dense network of over-the-horizon and low-frequency radars. In a contingency focused on Taiwan, the tyranny of distance becomes a weaponized variable. A sortie from Andersen Air Force Base in Guam to the Taiwan Strait covers approximately 1,500 nautical miles each way, a transit that demands 2 to 3 aerial refueling events for the current generation of tactical fighters. Those tanker orbits themselves have become high-value vulnerable targets, and their loss would effectively neutralize the combat range of a substantial portion of the U.S. fighter fleet. This strategic environment does not merely degrade the margin of error for individual pilots, it fundamentally rewrites the operational requirements for air superiority. The objective is no longer to maintain a continuous peacetime presence, but to generate temporary, localized windows of dominance deep within the most heavily contested and sensor-saturated airspace in human history.
The F-47 and the F-35 Block 4 are not sequential steps on a single ladder of fighter evolution. They are products of fundamentally divergent design philosophies conceived to solve entirely different problem sets. The F-35 Lightning II, even with the comprehensive computing and sensor enhancements of Block 4, remains a 5th-generation multi-role platform optimized for the broad aperture of strike warfare, coalition integration, and lower-intensity battlespace management. Its design was frozen in the 1990s under the mandate of the Joint Strike Fighter program, which sought to replace a wide swath of legacy airframes with a single software-definable and relatively affordable warplane. Its strengths lie in versatility and sensor fusion, but its physical traits, a single engine, a modest internal fuel fraction, and an airframe optimized primarily against high-frequency fire control radars, are immutable. The F-47, by contrast, is a dedicated 6th-generation air superiority system, engineered from the keel up as a penetrating counter-air asset. Where the F-35 is a tactical workhorse designed to operate with the support of a permissive logistics tail, the F-47 is an exquisite spearhead intended to survive and fight in isolation inside an adversary's weapons engagement zone. The distinction is not merely in generation but in function. One platform exists to expand the capacity of the Joint Force network, while the other exists to puncture the enemy's defensive network so that the rest of the force can flow through the breach.
Engineering analysis of the F-47's disclosed parameters reveals a system optimized to nullify the 2 primary constraints of Indo-Pacific combat operations: distance and multispectral detection. The platform's defining strategic attribute is a combat radius exceeding 1,200 nautical miles on internal fuel alone, a figure nearly double that of the F-35A. This range is enabled by a combination of a high fuel fraction airframe and a variable cycle or adaptive cycle propulsion system, which can cycle between a fuel-efficient high-bypass transit mode and a high-thrust, low-bypass combat mode to sustain speeds in excess of Mach 2. Just as critical is the shift to broadband signature management. While previous generation stealth designs were optimized to defeat X-band fire control radars, the F-47's tailless blended wing body configuration is a direct physics-based countermeasure to the VHF and UHF early warning radars that China has deployed in significant numbers. By eliminating vertical stabilizers, which act as prominent corner reflectors for low-frequency wavelengths, the platform dramatically reduces its radar cross-section across a much wider portion of the electromagnetic spectrum. However, the most disruptive capability embedded in the F-47 is its native architecture for manned-unmanned teaming. The aircraft is not simply a shooter, but a command node, equipped with onboard artificial intelligence processing to orchestrate a swarm of collaborative combat aircraft. These loyal wingman drones function as distributed sensors, electronic warfare jammers, and forward-deployed missile magazines, extending the sensory reach and strike envelope of the crewed aircraft, while allowing the pilot to remain farther from the highest threat densities. The F-35 Block 4 upgrade program represents the most ambitious software and mission systems overhaul in the platform's operational history, yet it remains an exercise in pushing a fifth-generation airframe to its logical limits rather than transcending them. The foundational enabler for Block 4 is the Technology Refresh 3 hardware suite, a new integrated core processor and memory architecture that provides the computational headroom necessary to host advanced sensor fusion algorithms and expanded electronic warfare libraries. When coupled with the new AN/APG-85 active electronically scanned array radar, a gallium nitride-based system offering significantly greater detection range against low observable threats and improved electronic attack fidelity, the F-35 transforms into a more lethal and survivable tactical node. Block 4 also expands the weapons bay integration profile to include standoff maritime strike munitions, such as the long-range anti-ship missile and advanced beyond-visual-range air-to-air missiles. These enhancements ensure the F-35 remains a highly relevant and formidable asset for coalition operations, maritime interdiction, and the prosecution of defensive counter-air missions. Yet, the platform is bound by the iron laws of its original physical design. Its unrefueled combat radius of approximately 670 nautical miles is a profound strategic vulnerability in the vast distances of the Western Pacific, rendering the fleet deeply dependent on a tanker bridge that would itself be a primary target for Chinese long-range fires. Furthermore, while Block 4 software can improve how the aircraft processes data, it cannot fundamentally alter the aircraft's kinematic performance or its vulnerability to low-frequency radar detection, constraints that limit its utility as a first-day penetrating asset in a high-intensity peer-level conflict. The strategic balance of air power will be determined as much by industrial throughput as by the performance specifications of individual aircraft, and on this metric, the United States faces a disquieting asymmetry. The U.S. defense industrial base, despite its technological preeminence, operates at a peacetime cadence that is ill-suited for the attrition rates of a prolonged peer conflict. The F-35 production line in Fort Worth, while globally distributed and sophisticated, yields approximately 150 to 160 airframes annually for the entire international partnership, with U.S. Air Force procurement for its own fleet hovering at fewer than 30 airframes per year in recent budget cycles. Contrast this with the Chinese model, which is characterized by state-directed expansion and the application of commercial manufacturing techniques to military aerospace. Satellite imagery analysis confirms that the Chengdu Aerospace Corporation has expanded its J-20 production complex by millions of square feet, operating multiple pulse line assembly facilities that produce an estimated 100 to 120 J-20 stealth fighters annually for the exclusive use of the People's Liberation Air Force. This raw output, when combined with capacity for the J-35 and advanced fourth-generation derivatives, positions China to field a combined fifth and future sixth-generation aircraft numbering well over 1,500 airframes by the early 2030s. The F-47, with an estimated unit cost 3 to 4 times that of an F-35 and a projected fleet size of approximately 200 aircraft, will be an exquisite asset of the highest quality. But in a battle of numbers, it is a low-density, high-demand force that cannot sustain significant attrition. This industrial reality compels a U.S. force design that compensates for a deficit in crewed airframes by accelerating the fielding of attritable, lower-cost collaborative combat aircraft to create mass. The Chinese response to the U.S. Next Generation Air Dominance program is neither a crude copy nor a simple catch-up effort. It is a coherent, multi-track ecosystem designed to contest American air power across the entire spectrum of capability generation. The Chengdu J-20 Mighty Dragon has matured from a developmental airframe into a credible long-range air superiority asset, with the indigenous WS-15 engine now equipping production aircraft and providing the supercruise capability and high-altitude kinematics necessary to threaten current U.S. fifth-generation fighters. The fleet size, which has already surpassed 400 airframes according to open-source assessments, provides the People's Liberation Army Air Force with a quantitative mass that allows for distributed operations, higher sortie generation rates, and a margin for attrition that a smaller, more expensive U.S. fleet cannot easily replicate. Furthermore, the fielding of the two-seat J-20S variant signals a doctrinal evolution toward dedicated battle management and the command of loyal wingman drones, mirroring the manned-unmanned teaming concepts central to NGAD, but executing them within a production-scalable airframe. The most striking signal, however, is the accelerated iteration evident in China's sixth-generation prototyping. The appearance of the tailless tri-jet J-36 and the visually distinct J-50 within a span of months demonstrates an industrial ecosystem capable of compressing the traditional Western development cycle. This willingness to build, fly, and adapt prototypes rapidly suggests that the People's Liberation Army is not waiting for a perfect final design, but is instead learning by doing, at a velocity that challenges the more deliberate, milestone-driven rhythm of U.S. acquisition.
The survivability of stealth aircraft in the 2030s must be evaluated against a threat environment defined by transparency, saturation, and multi-domain convergence. The historical advantage conferred by X-band low observability is being eroded by a proliferation of low-frequency VHF and UHF band radars, exemplified by the YLC-8B towed arrays deployed along the Chinese coast and on outposts in the South China Sea. These sensors exploit a physics phenomenon known as resonance scattering, where the radar wavelength approximates the physical dimensions of an aircraft's control surfaces, effectively bypassing shaping features optimized for shorter wavelengths. While such radars lack the angular resolution to guide a missile to impact, they provide tactically relevant early warning and cueing, vectoring advanced interceptors equipped with sensitive infrared search and track systems to a target's approximate location. This terrestrial sensor grid is integrated with a proliferating space-based intelligence architecture, including the Jilin-1 constellation, which offers high revisit rate electro-optical coverage and a potential look-down capability against thermal and visual signatures. Massive salvos of anti-ship and anti-air missiles complicate the defensive geometry, forcing defensive counter-air assets to expend limited magazine capacity against numerically superior inbound threats. The battlespace is further saturated by waves of lower-cost one-way attack munitions and drone swarms designed to overwhelm traditional defense systems and expose the electromagnetic signatures of high-value sensors. Ultimately, the threat is not a single radar or missile, but a layered, redundant system of systems that compresses the decision space and forces any penetrating aircraft to rely as much on network resilience and autonomous decoys as on pure stealth shaping.
A comparative analysis of the F-47 and F-35 Block 4 yields a conclusion that transcends the binary question of platform superiority. The two systems are not competitors vying for the same budget line. They are mutually dependent components of a hierarchical air power construct essential for any credible campaign in the Indo-Pacific. The F-47 provides a unique capability that no software upgrade can retrofit onto the F-35, the ability to penetrate deep inside a mature, multispectral, integrated air defense network without immediate reliance on a fragile and predictable tanker bridge. It is the necessary instrument for creating the localized, temporary windows of air superiority required for the joint force to maneuver in a denied environment. Conversely, the F-35 Block 4 provides the breadth, mass, and distributed sensor coverage necessary to exploit those windows, executing maritime strike, suppression of enemy air defenses, and persistent intelligence collection. The F-35 ensures that the United States and its allies do not fight as a collection of individual aircraft, but as an integrated high-volume sensor shooter grid. The greater strategic vulnerability lies not in the technical specifications of either airframe, but in the capacity of the U.S. acquisition system to field both platforms in sufficient numbers and on a timeline relevant to the growth trajectories of the People's Liberation Army Air Force. Victory in a future Pacific conflict will belong to the side that best orchestrates the interplay between exquisite 6th-generation command nodes, ubiquitous 5th-generation mass, and the attritable foundation of autonomous unmanned systems. The F-47 is the spearhead, the F-35 is the shaft, and neither is useful without the other, or without the warrior wielding them.